So have a look at page 6 of your worksheet. This is November 15 P43, where the first question requires you to define what is meant by simple harmonic motion. Okay, so for the first part here, define simple harmonic motion, you can actually just copy back the definition from the notes where you say it's a periodic motion in which acceleration of the body is directly proportional to displacement from a fixed point, and the acceleration is always directed towards that fixed point itself, worth 2 marks. So you don't want to write that, you can actually just always write acceleration is proportional to distance from fixed point, and acceleration and displacement are always in opposite direction. These are the two main points that are required inside your marking scheme. Okay, then after that you move on to part B here. They told you that there's a tube sealed at one end that has circular cross-sectional area A of 4.9 times 10 power minus 4 meters squared. Some sand is now put in the tube so that the total mass M of the tube and its contents is 70 grams. The tube floats upright in a liquid as shown in the figure below. And then subsequently, they mentioned that the liquid here has a density rho of 0.79 gram per centimeter cube. Now, by reference to the liquid pressure exerted on the base of the tube, show that the distance h of the base of the tube below the liquid surface is 18 centimeter, and explain your working. So there's a specific phrase here in your question which asks you to make reference to the liquid pressure exerted on the base of the tube. Okay, from there you're supposed to show that the distance h, which is this one, is 18 centimeter. So what you can do from there is to recall something that you would have learned from your AS before this, specifically the forces, density, and pressure chapter. So it was mentioned to you before that pressure at the same depth or height for the same liquid is always the same. Or maybe I should just write this. Pressure between 2 points at the same depth for the same liquid will always be the same. So you're trying to apply it for your current case here is something like this now. This is another separate draw out of the existing diagram. So let's just consider this particular depth here, where you have point A and you have point B. Okay, you have point A and B here. So because they are at the same depth from the surface and you're talking about the same liquid, you could say that pressure at point A is going to be the same as pressure at point B. Now, pressure at point A over here is the pressure due to the liquid above that point. So I can say that pressure at PA is the pressure of the liquid. But if I'm talking about pressure at point B here, it's actually the pressure exerted by whatever is above it. This is the pressure exerted by the tube. Okay, so this one, the pressure at point B is the pressure due to weight of the tube, due to weight of the tube above it, due to weight of tube above. So this one, pressure at point B is the pressure of the tube. Okay, so pressure at A is the same as pressure at B. I can say pressure due to the liquid is same as pressure due to the tube. So for pressure due to liquid, I can expand it to become H rho G. This is something that you have learned in the AS chapter before this. Whereas pressure of your tube, this one I have to make use of the original equation from pressure, where you say that pressure is actually force over area. So right now, if you're talking about the weight of the tube above that point, it's just going to be mg divided by area to get you your pressure there. Okay, so this is your resulting equation, and there are certain things that will cancel off, especially your g. Your gravitational acceleration g, you will notice it tends to cancel each other off, eventually leaving you with h equals to m over rho A. So right now, you want to sub in all the values. Your mass, capital M, is already known. They already told you the mass somewhere earlier in the question. They told you that it's 70 grams. This is your mass, big M. Okay, so this one you have to change it to kg. So it's 70 times 10 power minus 3. And then your density. Now your density is the one that may be a bit of a problem here because it is in grams per centimeter cube. So it will be a good idea to change it to kg per meter cube. So if you have 0.79 grams per centimeter cube, it means you have 0.79 grams for every 1 centimeter cube. Okay, so what you want to do now is that you want to change this to kg, you want to change this to meter cube. Okay, so if you want to change from centimeter cube to meter cube, 1 centimeter cube is the same as you saying that there's 1 centimeter inside a bracket that is cube. Change whatever is inside the bracket. That one would have been 10 power minus 2 meter. And then because it's inside a bracket, it will have to be cube eventually. So that this one becomes 10 power minus 6 meter cube. So when you want to change your centimeter cube to meter cube, you just need to multiply with 10 power minus 6. So the bottom one here would just be 10 power minus 6. Whereas the top one here, because you're changing it from grams to kg, you just divide by 1000. So that eventually you get 790 kg per meter cube. So that is the value of density that you want to use here. And then as for your area, the area is already stated already. It's going to be 4.9 times 10 power minus 4. So just put that value in. You will eventually get the answer as 0.18 meter, which is eventually the same as 18 centimeter. So this is now shown. Okay. Then the next part will be more directly related to what you've learned in this chapter. So here they mentioned to you that the tube in B is displaced vertically and then released. The variation with time t of the distance h is shown in the figure here. The system oscillates with simple harmonic motion of angular frequency omega given by this expression here. So where g is the acceleration of free fall. Use the data from B to determine time t1 as well as time t3. This is the question that they want you to do. Okay, they need you to determine time t1 and then time t2. All right. So if you look at the question, specifically the graph, t1 is over here, whereas t3 is over here. Now, if you look at the graph, you should be able to identify what is one cycle here. If you look at the graph, this part here is already going to be one cycle corresponding to one period. Okay, so if you're talking about T1, which is this one, it is actually corresponding to half a period. Okay, so this one is actually going to correspond to half a period, which is just half T. Okay, and then how about for T3? So you look at T3, T3 is right over here. You try to extrapolate the line out, you will notice that this is actually another half cycle. So going from here all the way to here, it will actually be 1.5 cycle. Okay, maybe this one I should write there as 1.5 cycle. This is 1.5 cycle. So it's going to be 1.5 t. Whereas the one below this originally, this one was actually half cycle or 0.5 cycle. Maybe I just write it as this. This one is 0.5 cycle. So it's going to be 0.5 T. Okay. So T1 is 0.5 T of the period. T3 is 1.5 T of the period too. You want to find the period here, which you can find from this given equation here. If you remember, omega angular frequency is 2 pi over T. You need to put it inside here and find out what is T. Okay, so for a start, you use that equation. Omega square is rho ag divided by m. Substitute omega as 2 pi over T. Make sure you square it. And then sub in all the relevant values, the density, the area, the gravitational acceleration, and then finally the mass. You should be able to get your period as 0.853 seconds. Okay, so in your case, your density here, this one is 790 kg per meter cube. You already actually kind of did the workings in the previous question. They gave you in the density in grams per centimeter cube, but you actually did change it to kg per meter cube already in the earlier question. So you can just use that value straight. So the rest of them is just a simple conversion if they're not in SI units. So your period being 0.853 seconds, T1 would thus be half your period. Just half the value you will get the final answer is 0.427 seconds. Okay, so pretty straightforward question for 3 marks. Then after that, if you then want to get time T3 in turn is just going to be 1.5 T. So put in the values, you will get the final answer as 1.28 seconds. All right, so this is pretty straightforward. Okay, now next comes the part 2 here, where you are supposed to determine the total loss in energy of the oscillating system between 0 and T4. Okay, so let's just have a look at your diagram first. They're talking to you about the energy loss between T equals to 0 seconds and T4. That would have meant this point here and this point here. You want to determine the energy loss between these 2 points. So to find the energy loss between these 2 points, you have to relate back to the total energy of oscillations, which you derive in the previous lesson as half m omega square x naught square. Okay, this one was actually under page 11 of your notes from before. Total energy is maximum kinetic energy, which works out to half m omega square x naught square. Okay, so you want to apply your equation to this situation here. You want to find out what is your energy loss E1 here, as well as your energy loss E2 here. Okay, but you need to be careful now. You know the value of your mass. You could find out the value of your omega from 2 pi over T. And you also need to find out the value of your amplitude. But the common mistake that people always do here is that they mistake the values over here as the amplitude directly. There is actually a trick inside your current question that you need to be aware of. The first thing to note is that your current graph is not a graph of displacement versus time. Okay, displacement in your current chapter is measured as distance from equilibrium position, is measured from equilibrium position. But your graph that you have right now in your question is something called distance h. Okay, now look at the previous page. What is actually distance h in the first place? Distance h is not measured from equilibrium position. This was your distance h. distance h of the base of the tube below the liquid surface. Okay, so here, when you're talking about your distance h is actually measured from the liquid surface, not from equilibrium. Okay, so the graph that they gave you here is actually a graph of distance h versus time, not graph of displacement versus time. If you're having a graph of displacement versus time, the displacement, strictly speaking, must be measured from the equilibrium position itself. So right now, if you have a graph of h versus time, you want to get amplitude so that you can use this equation. You cannot read this value directly that you have here. Neither can you read the value directly here. You have to do something with it first. So your amplitude for E1 or X1 here is actually the difference between these 2 points. You see your H here, you notice that it didn't start from 0. So this one here, if I read it correctly, is actually supposed to be 20.2 minus 18. Distance X1 is supposed to be 20.2 minus 18, giving you 2.2 centimeter. This is your amplitude for X1. Then for your second point here at T4, you get the difference between these 2 points. This one would give you amplitude for 2 being 19 minus 18 equals to 1 centimeter. So why do I have to do this in the first place? It might be easier if you try to visualize it like this. If you consider how your cylinder was oscillating, say maybe this one was the top position. Maybe this one was the top position. Maybe this one was the equilibrium position. And then maybe this one was the bottom position. If this one was your liquid surface, this one here, your distance h, would all be measured like this. This one will be measured from the top surface. This one will be measured from the top surface. This one will also be measured from the top surface. So when your cylinder was oscillating, your reference point was always from the top surface. At the top position, this is your value of h. At the equilibrium position, this is your value of h. At the bottom position, this is also your value of h. Okay, but this is not your displacement as I mentioned to you. So to get your displacement, it must be measured from equilibrium position. So think about it. If this point here is actually your equilibrium, and then this point here is your bottom position, and this point here is actually a top position. When you're talking about your amplitude, it is really this one or this one. Okay, to get your amplitude position for this function here, you take this height minus this height. This one will give you your amplitude. Okay, maybe it's better if I show it as here. Okay. If you want to get your amplitude position, you take the difference between these two heights. And then if you want to get another different amplitude position, let's just say the bottom amplitude position, which again should be measured from your equilibrium, you again will take the difference in the heights. Say in your case, you take the difference between this height and this height so that you can get this amplitude position. Okay, so that's why here you notice that to get your amplitude, you are really taking the differences between the two heights. Once you have that, you can now use your equation. right? Because what you're really missing is really just the amplitude positions. You now look at your workings. Your x01, let me write it here. Your x01 is actually 2.2 centimeter. Your x02 is actually 1 centimeter. Okay, so total energy loss is E1 minus E2 is half m x01 square minus half m x02 square. The half m omega square can be factorized out, and then multiplying with the x01 square minus x02 square. So the mass you know as 70 grams, so change to kg is going to be 0.07. The omega you do not know directly, but you do know that omega can be 2 pi over t. So you just found out what was t before this. It was actually 0.853. So you sub that in also here. It's 2 pi over 0.53. Square the term. Then after that multiply with the difference in your amplitude square. So this one you have to remember to change it from centimeter to meter. So this one is 0.022 square minus 0.01 square. So your total energy loss eventually works out to 7.29 times 10 power minus 4 joules. Okay, so this is your working here. Next question that you can have a look at is page 17. Okay, page 17 is November 2016 P42. So for this question here, if you look at it now, they mentioned to you that you have a mass that hangs vertically from a fixed point by means of a spring as shown in the figure below. The mass is displaced vertically and then released, and the subsequent oscillations of the mass are simple harmonic. The variation with time t of the length L of the spring is as shown. Okay, so this one here, you will notice is actually not displacement from equilibrium. It's actually measuring the length of the spring. So whatever you see here right now, the graph is a wavy shape showing that it's oscillating, but it's not a graph of displacement versus time, okay? But rather a graph of spring length versus time. So this is one thing to be careful about. So from there, for the first part of your question, they ask you to use the figure and state two values of t at which the mass is moving downwards with maximum speed. Okay, so in your case, you do see a wavy shape here indicating that the mass is oscillating. So if you were to try and determine where is your equilibrium position, it should be right in the middle here, isn't it? Because this is say 17 and this is 13. The difference between them is actually 4. So the middle should be about 2 centimeters above and below. So that means this is your equilibrium position. Okay, so this is your equilibrium. Let me just draw it out. This part here would be considered as your equilibrium position. Okay, so one of the things that you may have learned in your wave section of AS was that particle speed, or rather just in your current chapter, Simple Harmonic Motion, we always say that maximum speed is at equilibrium. This is something that we've learned in AS waves and also A2 Simple Harmonic Motion. Maximum speed is at equilibrium. Zero speed is at amplitude. So in our case, max speed is at equilibrium, but zero speed would always be at amplitude. Okay, so this point here being our equilibrium, or rather this line here being our equilibrium, we would know that our speed is always going to be Vmax here. Okay, But the question specifically wants the part where you have maximum speed downwards. So how are we going to know which of this is actually going to be maximum speed downwards? Because you could have either this point, this point, this point, or this point. All of these are considered to be maximum speed. But how do I know which one is actually maximum speed downwards? So one of the things to note was that this is a graph of spring length versus time. So if you try to imagine it right now, how your spring would look like as your mass oscillates, this one could be, say, your top position, like this. This one, say, could be your equilibrium position. And this one here, finally, could be your bottom position. Okay, so your lengths are always measured with respect to your fixed support here. They are not measured from your equilibrium, okay, according to what your question is described here for you. So say right now, you look at this, let me just try and draw it out again. This one here being equilibrium. This one here being the top position, and this bottom. This one here being your top. This one here being your equilibrium. Okay, so these are the relative positions of everything. So think about it. At the top position, this is the length. This is, let's say, L1. And then at the equilibrium position, this one will be your length. This is L2. And then at the bottom position, this is your length also. This is L3. Okay, so the length at bottom usually should be more than the length at the top. Okay, based on this diagram. So right now, you look at your current graph. This one is a graph of spring length versus time. Okay, so notice that when you reach amplitude positions, this part here is having a value of 17 centimeter, whereas this other part here is having a length of, say, 13 centimeter. Okay, so the one with the longer length should be your bottom position, whereas the one with the shorter length ought to be your top position. You can actually clearly see this from your diagram if it's drawn like this. The one with the shortest length is actually you at the top position, whereas the longest length is actually you at the bottom position. And then the one in the middle somewhere is going to be your equilibrium. Okay, so you know these two positions right now, where they are. So you consider this now. If you move from here to here, this one means you're going from bottom to up. You're moving upwards. But from here to here, you're going from top position to bottom. This one, you're moving down. And then this one, again, it repeats itself from bottom to top position, you're moving up. Whereas this one, you're moving from top position to bottom. This one is you moving down. So the one where you get maximum speed downwards is actually going to be this one. These are the times that you want to pick up. It's going to be 0.225 as well as 0.525. That's how you pick out the answer here. Okay, so that's for this part. And then let's just say from this diagram, I want to determine one thing further. I want to determine the amplitude of the oscillation. So the amplitude of oscillations cannot be read directly from these values. You have to subtract two different values to get the amplitude. If I wanted to get the amplitude here, this one is actually 17 minus 15, giving me 2 centimeters. The same could also be said for the bottom amplitude. Amplitude here is actually 15 minus 13, giving me 2 centimeter. This is my amplitude. Because here, if I wanted to relate it to my diagram, this one, my A, is really just L2 minus L1. Whereas this one, my A would be L3 minus L2. It's always the difference in the length between your amplitude position and the equilibrium position. That one will give me my amplitude itself. You will make use of this amplitude value in the subsequent calculations. If you move on to the next part of the question, they ask you to determine for these oscillations the angular frequency. So angular frequency is something that you've already learned before. It's defined as omega equals to 2 pi over t. So just read out the value of your period from your graph. You can see that this one is actually 1 period here, and the value is going to be 0.3. Okay, so this one here is 1 period equals to 0.3 second. So just sub in the values, 2 pi divided by 0.3, you will get the answer as 20.9 radian per second, just like that. Okay, and then after that, for the next part, show that the maximum speed of your mass is 0.42 meter per second. So Vmax, as you learned in the previous lesson, is actually omega x naught. The velocity at any point is always v equals to omega square root x naught square minus x squared. But Vmax would always be omega x naught. Because Vmax when x equals 0. So this part here, you really just equate to 0. It will simplify to the expression that you see below. Okay, but you don't need to show the derivation. You just straight away can say that omega x naught is your Vmax. So your omega you just found is 20.9. Your amplitude just now actually did indicate in your diagram is actually 2 centimeter. Remember to change it to meter. It's 17 minus 15 centimeter, giving you 2 centimeter. So your final answer will be 0.418 meter per second. Round it up to 2SF, you're going to get the answer. Okay, so that one is for this one. Right, then the next part here is for the part where you need to draw a graph. So in your case, you want to draw a graph. They say that use your data from figure 4.2 and A3, which is the one that you just done. On the axis of figure 4.3, the variation with displacement x, form the equilibrium position or the velocity v or the mass. They want you to draw a Vx graph. Okay, so when it comes to your Vx graph, it's always going to be some sort of circular looking or oval looking graph. So, but usually you need to plot out 4 specific points first. So what you do know is that when it comes to velocity, maximum speed is at equilibrium. This means that x is 0. Okay, so this one maybe I just use this back. V maximum speed is at equilibrium. This means that V max when x is 0. And then you have 0 speed at amplitude. This in turn means V is 0 when x equals to positive, negative x naught. Okay, these are the two most important information to always remember. When you have max speed at equilibrium, that means when x is 0, V is max. When you have 0 speed at amplitude, this means V is 0 when you have positive and negative amplitude. Okay, so you will mark out those 4 points here. If you're talking about the first condition and x equals to 0, you have V max. You already know the value of your V max at 0.42, so just mark it out accordingly on your graph. And then after that, you also know that at amplitude position, you are going to have 0 velocity. In your case, your amplitude, you did find it out as 2 centimeter. This is the part where you are supposed to use your data from figure 4.2 to find out your amplitude, and that it was actually 2 centimeter. So at 2 centimeter here and here, make sure that the velocity is 0. Okay, so once you have drawn out those 4 points, just join those points together using curves. Okay, don't ever use straight lines, right? Because the equation doesn't seem to indicate it's a straight line. Because there's a square and a square root term, it definitely will be some sort of curve, right? So that's for this question.